Hi, in this video I'm going to discuss tree ADT and binary search tree. For the contents of this presentation, we have what is a tree ADT, the definition of tree ADT, the different types of binary trees, and also the operations that you could use when dealing with binary trees. So first, let us define what is a tree ADT. So trees are similar to a linked list, but instead of each node pointing simply to the next node or previous node in a linear fashion, each node points to a number of nodes. Okay, let's say for example we have here node A. So node A points to node B and at the same time points to node C. So same goes for node B. It has a multiple uh, node. So B points to D, points to E, points to F. Okay, so it has multiple connections to different nodes. Now here are some some terms that you could use when dealing with a tree. So the root of a tree is the node with no parent. There can be at most one root node in a tree. Here in our diagram, the root node is node A since it doesn't have a parent. Unlike B and C, so the parent of B is A, the parent of C is A, the parent of J is G, the parent of K is G, and G has also a parent C. Okay? Now, an edge refers to the link from parent to child. So you see this yellow line here, this is the edge. It connects the parent to the child node. Okay? So the next one, a node with no children is called the leaf node. In our example, the leaf nodes are H, I, F, J, and K. So they don't have a children. Children of same parent are called siblings. B and C are siblings of A. D, E, F are siblings of B. B and C are siblings of node A. D, E, F are siblings of node B. Okay? So the next one is, so here's a notation. So node P or a node P is an ancestor of node Q if there exists a path from root to Q and P appears on the path, and let's say ACG are the ancestors of K. So as you can see here, as we traverse to K from A, the ancestors of K is ACG because there exists a path that connects from the root node to the node Q. Okay, so ACG is the ancestor of K. ABE is the ancestor of I. A, B, and D are the ancestors of H. Okay? So now the set of all nodes at a given depth is called the level of the tree. Okay? So we have here the level of the tree. B and C are the same level. So they are level 1. The root node is at level 0. So at the topmost side of this example, so node A is at level 0, and then level 1, B and C, so D, F, G is level 2, and then level 3, H, I, J, K. Okay, so the depth of a node is the length of the path from the root to the node. So the depth of G is 2. So here we can see that this is G. Okay, so from the root we could just count 1 and 2. So it's just like the level, right? So from root traversing to G, so we have 1 and then 2. So that's the depth of this node G. Okay, so next, the height of a node is the length of the path from that node to the deepest node. So let's say, for example, the height of C is 2. Okay, so the depth or the deepest node here is either H, I, J, and K. Okay, so since C belongs to this path, so we could conclude that from K to G is 1, G to C is another 1, so 1 plus 1 is 2. So that's why the height of C is 2. Now the height of a tree is the length of the path from that node to the deepest node. A rooted tree with only one node, the root itself has a height of 0. So let's say, for example, we only have one root node, or let's say the root node itself. So this has a height of 0. But if this one has, let's say, have a child nodes or children, so it has 1. Okay, so the height is 1. Now the size of a node is the number of descendants it has, including itself. So let's say, for example, the size of the subtree C. So this is the subtree C is 4. So 1, 2, 3, and 4. Okay. So next, if every node in a tree has only one child or none, then we call such trees skewed trees. So this is a skewed tree. Now there are two types of skewed tree. So we have here, if every node has only left child, then we call them left skewed trees. Okay. So let's say, for example, from A or node A, it has the left hand side tree or child, and then this child here also has a left child, so this is a left skewed trees. So similarly, if every node has only right child, then we call them the right skewed trees. So as you can see here, the skewed trees have a one child. Okay, so it has a one child from the left, and then this child also has one child with from the left side or right side, and then left. Okay, so it's not totally a left skewed tree. At the same time, it's not a right skewed tree. So that's why it's only a skewed tree. Okay. So here we have another type of tree. Okay, which is the binary tree or binary trees. So a binary tree is called, or a tree is called a binary tree if each node has 0 child, 1 child, or 2 children. So empty tree is also a valid binary tree. So we can visualize a binary tree as consisting of a root and 2 disjoint binary trees, so called the left and right subtrees of the root. So for just a visualization, I have here, let's say, for example, the root node. This is the starting point, and if it has a left child, then this is a separate tree from the right subtrees. Okay, so these two are disjoint. They are not they are connected via root. Okay, so there is a edge connecting to the root, but these two subtrees are disjoint. Okay, so an example is this figure on your right side. So we have here a root node 3. Okay, so we can visualize this as the root node is 3. Okay, and then it has a left child and then right child. So this one at the left side or left child, it has a right child node. Okay, now we have different types of binary trees. Okay, so you could imagine that these trees are the data structure of a tree. Okay, so we have here the first type, the full or strict binary tree. So it is a binary tree or a binary tree is called a strict binary tree if each node has exactly two children or no children. So regardless of the level, we have here the root node, and then this root node here has a two children or has a children. Okay, and then this children here also has a two children, and then again. Okay, or it could have no children. Okay, just like this one. So that's why this is a full or strict binary tree. Another one is this figure. So the root node has two children, and then these two children has no children. So that's why this is a full or strict binary tree. Now another one is the perfect binary tree. So these are the nodes, or the nodes contain two children and all leaf nodes are on the same level. Okay, so don't be confused with full binary tree and perfect binary tree. So as you can see here, a perfect binary tree, it tells us that all the leaf nodes are on the same level. So as you can see here, these are the leaf nodes, the one without a children. Okay, now the main difference between full binary tree and a perfect binary tree is that this full strict binary tree has a child node, okay, a child node at level 2 and at level 3. So this is the left side subtree, no, left subtree. Okay, and if you compare it at the right subtree, this right subtree only has a level 1 leaf. This is level 1, this is level 2, and then this is level 3. So that's why this one cannot be considered as a perfect binary tree because all of its leaves are not on the same level. Unlike perfect binary tree, all leaf nodes are on the same level. Okay, so that's the difference between these two. Okay, so now next we have here the complete binary tree. So all levels except the last level is filled. So last level should be filled from left to right. Okay, so in order for us to check if a binary tree is complete, so let's just say we label each node from the root node. Let's say for example from the root node it has 1, and then the child of 1 is 2 and 3 and 4 and 5, so in sequence. So as long as there's no missing number from here, so this is a complete binary tree. So we filled it from left to right. Okay, now for the case of, let's say for example, this complete binary tree here, we remove this part. Okay, we remove this part. Remember that it should be filled from left to right. As you can see here, the numbers are not in sequence. 1, 2, 3, 5. The 4 is missing. So this is not a complete binary tree. Now, another thing or another example, we have here 1, 2, 3, 4, 5, 6, 7. Okay, now if we remove 4 and 5 from our left subtree, as you can see here, the numbers are not complete. 1, 2, 3, 6, 7. So this is not a complete binary tree. We need to fill first the left subtree in order for us to make it a complete binary tree. Okay? So with that class, we can conclude that a binary tree can have a one or more types. Okay? It could be a perfect binary tree and at the same time a complete binary tree. Okay? So there are two more examples or types of binary trees, the balanced binary tree and the pathological or degenerate binary tree. Okay, so here in a balanced binary tree, we need to find the solution first. No? So find the absolute difference between the height of the left and right subtree. So it should be less than 1, it could be 0, or equal to 1, or equal to 1, to consider it as balanced. So you could use this formula. So the difference is equals to the absolute value of the height of left minus the height of right. Okay, so we need to evaluate first inside the equation inside the absolute value. Okay, so now I have here two figures. Okay, so here we have the height of left. So consider this left subtree as the root. So this is the root, for example. So now the height of this left subtree is 1. So from the children, or from the child node going up, so this is 1. Okay, and then comparing it to the right subtree, okay, which has no children, so this is the root node, so it has 0. Okay, so note that the height of an empty tree is -1. Okay, so let's say, for example, here we have a missing node. We don't have a node here, so this is -1 and then -1. Now if we're going to compute this, so the height of the left subtree, or missing left subtree, is -1 minus -1. Okay, and then of course the absolute value. So we can see that minus sign, -1. Okay, -1 and then -1, this is +1, so this would become 1, or -1 plus 1 is equals to 0. So that's why this is 0. Okay, so let me erase this first. Okay, so the height of the left subtree, going back to our diagram, so the height of the left subtree is 1, the height of the right subtree is 0. So 1 minus 0 is 1. Absolute value of 1 is 1. So this is a balanced tree. Okay, remember, in our rule, it should be less than or equal to 1 to consider it as balanced. Now consider the next figure. We have here an obviously unbalanced tree. Okay, so we have here this left sub tree. So 1, 2. So considering that this is the root node, okay, so 1, 2. Okay, now this is the height of the tree. Now considering the previous example, so this is 0. Okay, so 2 minus 0 is 2. Absolute value of 2 is still 2. So 2 is greater than 1, so we could consider this, or we can conclude that this tree example is not a balanced binary tree. Okay, so that's it. Now for the next type of a binary tree, so pathological or degenerate binary tree, so the parent nodes have only one child node. So as you could remember, the skewed trees, so we have here a skewed tree. So it's really easy to determine if that's a pathological or degenerate binary tree. You only look at the parent node if they only have a child node, and if that child node only has uh, only one child node going to its deepest node, so that's a pathological or degenerate binary tree. Okay, so those are the 5 types of binary trees. Okay, so what operations can we use in a tree? So there are 2 types of operation: the basic operations and auxiliary operations. So these are the most commonly operations that are used in implementing a tree. So remember that tree is an ADT. So I'm not giving the implementation, but rather I'm just describing how it would work. Okay. So some of the basic operations of a tree is inserting an element into a tree, deleting an element from a tree, searching for an element, traversing the tree. And then for its auxiliary operations, finding the size of the tree, finding the height of the tree, finding the level which has the maximum sum, and then finding the least common ancestor for a given pair of nodes, and many more. Okay, so I would just leave this to you to search on how to implement these operations. Okay, and with that, thank you for watching this video.